Hello, this is my SPED talk on metaprogramming and symbolic reasoning in Julia, and my name is Joseph Olson. So, if you look at metaprogramming, the definitions you'll see is code that generates other code and generating code at compile time. So, an example that many people are familiar with are macros, and so we have an example of macros in C to the right. We have some macros at the top with a hashtag. And so we have an and macro, which basically says we're going to use this keyword and in our code. And then at compile time, we want to replace each instance with and with a double ampersand. So that kind of macro would make the code more readable for a user. Another example is at the third one, the third define, where they define condition one to be a is greater than 0 and b is equal to 0. So if that's used a lot and they want a more meaningful kind of word to put that in their code, because they don't want people to focus too much on what that actually says, but they want to just say that we're referring to condition one. Then that will kind of tell them that's the case. So why macros? So generating values compile time give us less compute during runtime. So even in C, macros can even be functions. So that if we want to if we know the value ahead of time at compile time, um, but it's not necessarily something that we know off the top of our head and we don't want to calculate ourselves, um, then that can be calculated for us during compile time and used throughout the program. Generating code is helpful for creating shorthanded tools that aren't implemented in the executable bytes. So that's like the and kind of macro we saw earlier. And more expressive code isn't limited to the language specification and the creation of domain-specific languages. So this is kind of one that we're going to dig into a little bit with more flexible metaprogramming. So more flexible metaprogramming, we usually refer to like languages like Lisp, languages that use their code as data. So that way, basically, um, I can turn code into a data structure, and then I can move around the keywords to change the data, to change the way the code looks. I can optimize the code within my program, and then finally evaluate the resulting code. And that can be all done within another program. Um, so produce some very powerful results. So an example of that, for those that are familiar with Python and the eval function, that takes a string of Python code and will return the result of the Python code by executing it. You could basically manipulate the strings however you want, and then finally you can pass the eval function, and it will run the code. So what is Julia? So I don't not have much time to read this, but Julia is one of my favorite languages that I really became more familiar with during my project. And this is listed from the julia.lane.org website of why Julia is so special. And I really think it's worth looking into for anyone that's interested. But yeah, I'll let you look into that. So now I want to talk about symbolic and algebraic reasoning. So really, this stuff can take a long time, but I'm just going to go over with kind of the big topics. So um, symbolic and algebraic reasoning is basically treating kind of um, data or kind of topics more as symbols rather than as kind of structures that we may be used to in manipulating them. So for instance, um, we might want a program to take the derivative of an expression, and instead of treating them like numbers or which to treat them like numbers, but instead of treating them like programs usually do, like maybe like bytes, and then using the CPU's implementation of adding two bytes together, we treat them as symbols, and we basically so when we want to take derivative, we just look at the first term, and then we take derivative of each term if it's like multiple terms in the sum, and then which basically say we take the exponent and then we decrease it, and then we put the exponent to be times that by the coefficient. That would be the derivative. So that would be symbolic because we're treating them more as symbols, kind of how we would do on paper, where we wouldn't really say like what is one, I guess on a byte. It's just a symbol, something we really don't really dig into. So that's one example. Code optimization is a use of symbolic reasoning. So you might write a program that runs through your program after it's written, and then replaces expensive code operations with equivalent operations that run faster. Domain-specific languages. So Catalyst.jl is an example. That's a library in Julia. It's domain-specific because it is made for chemists and is supposed to be more natural to use to chemists. So they kind of write out things symbolically as they would like on paper, and then it produces code that matches what they're familiar with. Another use is code verification, and you can write code that produces certain results symbolically by looking at the code, by looking at other code, and then it'll look at the code and it'll say what should be true at certain points in that code. And then so there's actually a language called Daphne that uses Hoare logic, which basically does kind of does just that, which basically says whenever you write an assert in a function, rather than just checking that assert passes every time that line is reached, at compile time, it'll try to prove that assert will always be true, and it can prove that for you, basically using Hoare logic and by looking at the code and producing these proofs. So these are two examples. So we have quote and Catalyst.jl. So quote is a kind of the metaprogramming power of Lisp, and that's kind of brought into Julia. So basically, like you can write 2 lines of code, and then you could say you can evaluate the code, and you could change the second line of code in some way, and they can reevaluate it. And you can do that more in depth by saying, well, not just change the second line, but I want to change I want to grab the second assignment value, and then I want to see what that is, maybe multiply by 3, and then put it back. And so Catalyst.jl, so this is the example I mentioned before. So this is domain-specific language built for chemists. So this is supposed to be kind of something, the kind of notation they're familiar with writing on paper, and make sense to them, and then kind of combine that with other kind of reaction networks they build, and then using terms they're familiar with, and it basically kind of turns that all into code for them. So MetaTheory.jl is what I use in the back end of my programming language for my project. So I just have one simple example. This is kind of a package in Julia that handles capturing rewrites, rules, and patterns. So it just kind of builds a lot of the useful metaprogramming that's very helpful for creating theories and the results and that are produced from those theories. So for instance, it's very helpful because we get to give math as a set of rules, a set of beginning rules like axioms, and then rules that can operate on those axioms. And then we get to give a lot of other topics like this. And so chemistry, like in Catalyst.jl, can be reduced to symbolic manipulation. Or even board games and chess. We could think of like, oh, queen, yeah, we can do different reasoning. And also MetaTheory.jl has something really neat, and it can prove simple equalities and inequalities. So an example I have here is just a simple use of MetaTheory.jl that optimizes code. And then so here we have a 2 kind of rewrite rules, scales or 2 functions, scale sum and sum prods. So they are equal, and we know that intuitively. And some compiler optimizers might even recognize that they're equal. But for more complex code, it might not recognize that they're equal. The compiler might not recognize that they're equal and recognize that one's faster than the other, or even that we want them to be equal. Like we may have a specific case where we know that these will always be equal, but the compiler can't assume that because it doesn't know the exact use case that we're using and the instances. So we can actually kind of force a rule here with MetaTheory.jl. We can say rule scale sum, and we can use these slot variables, which are basically saying for any a, b, and c, scale sum a, b, and c is equal to sum prods a, b, and c. And then we can have our code optimize in a quote block. And so whenever it sees sum prods, might have an instance of sum prods in there. And then we might have a code here that says check this code block. And then whenever we see sum prods, we want to rewrite it to scale sums. And so basically we have this reduce rule, And then so that would, this R is actually reduce. I just forgot to rename that. So we reduce this line, and if no reduce was fine, then it returns nothing. So it returns nothing, then you return the original line. If no pattern, if it didn't match the pattern, um, otherwise you return the new optimized code. So yeah, so that is kind of some simple examples of capabilities, and I think it's really cool, and I think it's something that's really worth looking into.